Let's work out some examples of Laplace transforms involving this new Laplace transform rule that we figured out for multiplication by a power of t. So let's find the Laplace transform of t squared e to the minus 3t. Now we could compute this using other Laplace transform rules. In particular, we could compute it as multiplication by an exponential in t gives us a shift in s, but I think it's interesting to use this other Laplace transform rule and see that it actually does give us the same thing. So multiplication by t squared on the inside on the outside of a Laplace transform should give us minus 1 squared times the second derivative with respect to s of e to Laplace transform of e to the minus 3t. So minus 1 squared is 1, so this part just goes away. So second derivative with respect to s. Laplace transform of e to the minus 3t is 1 over s plus 3. And so now we just need to take two derivatives here. First derivative is going to be what? Minus 1 over s plus 3 squared. And then one more derivative is going to give us, let's see, plus 2 over s plus 3 cubed. And if you work out the Laplace transform of t squared times e to the minus 3t using our shift formulas for the Laplace transform, this is indeed what you get. Right, you get multiplication by an exponential on the inside is a shift in s on the outside, so this is a Laplace transform of t squared, but then shifted s gets replaced by s plus 3, right, s minus the coefficient in the exponential, so minus 3, so s plus 3. Laplace transform of t squared is 2 over s cubed, and then we still have to replace s with s plus 3. Oops. And you do indeed get that, what we got doing it the other way. So it is nice to see that if there is more than one way to compute a Laplace transform, you do get the same thing either way. So let's look at another example. How about this one? Laplace transform of t minus 2 times cosine of t minus 2 times the step function of t minus 2. So with these shifts in this step, I hope it occurs to you that we should probably, the first thing we should do is turn this shift in a step on the inside into a multiplication by an exponential on the outside. So this is going to give us e to the minus 2s times the Laplace transform of t cosine t. Okay, now we can use our multiplication by t formula. So e to the minus 2s, multiplication by t on the inside turns into a minus sign and derivative with respect to s on the outside, times Laplace transform, or not times, but applied to Laplace transform of cosine t. And we know the Laplace transform of cosine t, so minus e to the minus 2s times the derivative of Laplace transform of t is, Laplace transform of cosine t is s over s squared plus 1. So this is minus e to the minus 2s, and then we have to do some quotient rule business here to compute this derivative. So let's see, s1 times s squared plus 1 minus s times 2s over s squared plus 1 squared. So these, those don't cancel. I take that back. So we get minus e to the minus 2s. And then we get, what, 1 minus s squared over s squared plus 1 squared. All right, there we go. Not too bad, so a little annoyance having to use the quotient rule here, but as far as computing the Laplace transform part, this transform formula made this part pretty straightforward. Okay, final example. Let's find an inverse transform here. So this inverse transform, it has this power right here is a little clumsy to deal with. So in this case, actually, we could deal with it by factoring s squared minus 4. But imagine if that minus in here were a plus. Here we would have a power of an irreducible quadratic, and we actually don't. Before now, we didn't have a way to deal with that. But now we do, because if you have an s in the numerator and an irreducible quadratic squared in the denominator, we can express this as a derivative. So this is going to give us a nice shortcut. So we need to take the inverse Laplace transform of, so this whole thing is the derivative of s squared, so 1 over s squared minus 4. So let me just double check that really quickly. So if I compute this derivative, right, I'm computing the derivative of s squared minus 4 to the minus first power. So the derivative of that is, it's going to be minus s squared minus 4 to the minus second power. And then the chain rule is going to spit out a minus, or a 2s. So it looks like, actually, I need a minus sign here. Okay. But a derivative in the s world and a minus sign, right, a derivative and a minus sign in the s world turn into multiplication by t in the t world. So we get t times inverse transform of 1 over s squared minus 4. And then to compute this Laplace transform, again, we could factor this this denominator and then do partial fractions and then take the Laplace transform of each piece. But it's actually nice to, it's worth remembering this particular inverse transform because it's kind of a common one. So it is, first of all, let's see, to make this work, we need a 2 in here, and that means we need a half out there. So we get over 2 right here. So the inverse transform of, right, this looks very much like the Laplace transform of sine, except there's a minus here instead of a plus. Well, it turns out that that gives you hyperbolic sine instead of regular sine, so hyperbolic sine of t. Again, if you factored the denominator and did partial fractions and then took inverse transforms, this is what you would get. You would get hyperbolic sine of t here. All right, so this trick using by expressing this as a derivative with respect to s, let us handle this awkward exponent in the denominator.